In this video, we're going to cover trigonometric substitution, which is a method for integration when you have integrands in a specific form. Trigonometric substitution can help us to integrate when we have a radical in one of these forms. If we have root a squared minus u squared, root a squared plus u squared, or root u squared minus a squared, again, we can use trigonometric substitution. So let's talk a little bit about it before we actually do it, just so we can kind of see our way forward. The first thing I want you to understand is the difference between a and u, because obviously I could have something like 16x squared minus 9, and I've got two patterns here that involve a subtraction, and so I need to know which one is 16x squared minus 9. Well, a is going to be some constant, whereas u is going to be some function that involves x. So in this example, 16x squared is a function, which means u, which is my function, is 4x, the square root of 16x squared. Whereas 9 is obviously a constant, and so I'm going to take the square root of 9, so a is 3. And obviously, this is the function I would use, and not this one, again, given the order of my two terms. The other reason it's important is because our u substitution is going to be different. So here I've got my u squared. What I'm going to end up doing is a u substitution for that function, and if it's in this form, my u is going to be a sine of theta. If it's in a squared plus u squared form, my u is going to be a tangent theta. And then if it's in u squared minus a squared form, my u is going to be a secant theta. The other thing to keep in mind is when we're dealing with all of these things, we're going to end up using our Pythagorean identities often. And so keep in mind that I've written them in one way. So cosine squared theta equals 1 minus sine squared theta. It could just as easily be sine squared theta equals 1 minus cosine squared theta. And I've written it secant squared theta equals 1 plus tangent theta, or sorry, tangent squared theta. I could say tangent squared theta is equal to secant squared theta minus 1. So any of those are okay for us to use for substitution. So let's take a look at our first example. In this first example, I have an integral that is in the form of root a squared minus u squared. And the rule, we already talked about the rule that we're going to let u equal a sine theta, but what I didn't tell you is then all of this is going to turn into a cosine theta. So let's take a look at that together, and I'm going to kind of go through this step by step by step, but you'll find that this step we're going to sort of know the answer before we get to the end of the step because they tell us what the answer will be. So for the first step, we're going to take x and we're going to find dx, because the big picture here is I've got this integrand and everything is in terms of x. And when I use trigonometric substitution, every x is going to be replaced by some expression in terms of theta instead. And then we're going to integrate in terms of theta, and then we're going to have to back substitute so that it's back in terms of x. So it's kind of a roundabout way of finding the answer, but it's effective because it helps us to get the answer. So again, my first step is to take the derivative of x. So if x is 4 sine theta, then in this particular question, dx is 4 cosine theta d theta. Step 2 is to simplify our square root. Whatever the radical is in our question, we're going to simplify that next. So I'm going to go through this one the long way. And again, I'm only going to be worried about the radical, so everything else I'm just going to keep there for now. So this is 16 minus x squared. And they've told us to take x to be equal to 4 sine theta. So now this is 16 minus 4 sine theta squared. So if I get 16 minus 4 sine I put squared twice, sorry, sine theta squared. So this is still 16. If I square the 4, that's 16. And if I square sine theta, I get sine squared theta. I can then simplify by taking 16 out of both terms, leaving me with 1 minus sine squared theta. I'm going to break this, because it's now a product, into two radicals. The first one is root 16, which obviously is 4. And the second one is 1 minus sine squared theta, which I'm going to replace with cosine squared theta. That's that trigonometric identity, Pythagorean identity. If I take the square root of cosine squared theta, I get cosine theta. So now I'm going to direct your attention back up here, where I said I'm already going to know the answer. If I look at this particular question, obviously A was the square root of 16, which is 4, and U was the square root of x squared, which is x. And this tells me if I'm using U to be a sine theta, which is what I did here, U was x, A was 4 sine theta, then it's always going to work out that the radical will reduce to a cosine theta. And is that true here? 4 cosine theta. So again, do I have to do the work for number 2? No, but I wanted to show you that that's how it's going to work every single time that you do it. All right, that brings us to step 3. Step 3 is to rewrite the entire integral in terms of theta. So I have the integral, and on the top I have 4, my numerator is 4. This is x squared, and so I'm going to replace x with 4 sine theta, and then I'm going to square it because it was x squared. Root 16 minus x squared, we already determined right here, is 4 cosine theta. And then dx is going to be replaced with 4 cosine theta d theta. So before I integrate, I'm going to reduce anything that I can. So I see that I have a 4 in the numerator, and I actually have, I'm going to go ahead and distribute that squared. I actually have 2 4s on the left side of my denominator, and so I'm going to cancel that 1 on the top with 1 of the 4s on the bottom. And then I also have a 4 here and a 4 here. One is a numerator and the other is a denominator. So all of the 4's cancel except for this one. And then I have a cosine theta in my numerator and in my denominator, so those cancel as well. And so what I'm left with is a 4, a sine squared theta, and a d theta. So simplified, this looks like 1 over 4 sine squared theta, d theta, which is closer to where I wanted to be, but I don't like a fraction ever. So I'm going to take this 1/4 out, and I'm actually going to integrate. This is 1 over sine squared theta. So how can I replace that? I can replace it with cosecant squared theta, d theta. So that's step 3. Step 4 is to integrate. So I'm going to actually now integrate 1/4 cosecant squared theta, d theta, and that's going to give me negative 1/4 cotangent theta plus c. So now we're trucking, and we're doing really well. This could be my final answer, except remember that I started this question up here with x's, and this is only my final answer in terms of theta. I now need to replace theta back into x's, so I need to do some back substitution. So to do that, I need to think trigonometrically. That's a fun word. Going back to x equals 4 sine theta. If I want to get sine theta by itself, I can divide each side by 4 and say x over 4 is equal to sine theta. And so if this angle, you have to choose one of the two acute angles in your right triangle to be theta, and it doesn't matter which one. So if I make theta that angle on the bottom left, then if I know that sine is x over 4 and sine is also opposite over hypotenuse, then the side opposite is x and the hypotenuse is 4. And then I can use the Pythagorean theorem to find the missing side of my triangle. And so the missing side of my triangle is that, I'm just going to call it b. b squared plus x squared is equal to 4. And therefore b squared is equal to 4 minus x squared. Oh, I did that wrong. 4 squared, so that's 16. 16 minus x squared, and then that means b is root 16 minus x squared, which should look pretty darn familiar to you. So this guy is 16 minus x squared. So why did I have to do all of that? It seems kind of silly. But, I'm sorry, this is step 5, is to make your little triangle. And then step 6 is going to be to use your little triangle that you've just created to evaluate the cotangent of theta. So if we think about cotangent, we know that tangent of theta, based on this triangle, would be opposite over adjacent. So x over 16 minus x squared. So that means cotangent of theta is the inverse, or the reciprocal. 16 minus x squared over x. So what is my final answer? My final answer is -1/4, so I'm going to put the negative out front. I'm not even going to put the 1 on top, I'm just going to put this because I'm replacing cotangent of theta with that expression. So 16 minus x squared. My denominator has a 4 and an x, and then plus c. So that is my final answer. And I guess to be a little bit more precise, I would say the integral of 4 over x squared root 16 minus x squared dx is equal to negative, oh, messing up, can't get my eraser to work, negative root 16 minus x squared over 4x plus c. This is my final solution. Let's try one now with a different pattern. So this pattern is also subtraction, just like our last example, but this one has my function occurring first. So looking at my radical, I can see that u would be the square root of x squared, which is x, and a would be the square root of 25, which is 5. And again, this is giving us sort of the keys to the castle. It's saying, hey, you're going to let u equal a secant theta, and if you do that, then your expression is going to be a tangent theta. And that is where u is greater than a. So we don't really know what x is, but we're going to assume it's greater than a. So let's go ahead and see how that goes. The first step, just like on our last question, is to find dx. So again, they've given us, it says for this question, use substitution, x equals 5 secant theta, but it doesn't matter if they told us that, because again, the instructions say let u, which is x, equals a, which is 5 secant theta. So they gave it to us, but they didn't have to because we're smart enough to do that ourselves. But then I do need to find dx, so I need to find what is the derivative of 5 secant theta, and that is 5 secant theta tangent theta d theta. That's step 1. Step 2 is to simplify your radical. And when I simplify my radical, I can do all of the work like I did last time, or I can just take the easy way out, which is what I'm going to choose to do this time. This tells me that x squared minus 25, without doing all of the work I did last time, is a tangent theta. So a is 5, so that's 5 tangent theta. So I'm not even going to do all of the work, I'm just going to use the pattern. Step 3 is to rewrite my integral in terms of theta. So my integral has a numerator of 5 tangent theta, has a denominator of x, and if you'll recall, x is 5 secant theta, and dx is 5 secant theta tangent theta d theta. So what can I cancel? I can cancel 1, 5, I can cancel a secant, and everything else is what I have left. So this is now the integral of 5 tangent squared theta d theta. So far so good, but I don't have an easy answer for the integral of tangent of theta. So I'm going to bring my 5, well, let's go ahead and put it underneath here. I'm going to bring my 5 to the outside, and I'm going to replace tangent squared theta with secant squared theta minus 1 d theta. So why did I do that? Because now I can actually integrate, which is step 4. I'm going to leave my 5 on the outside. If I integrate secant squared theta, hopefully you know that the integral of that, the antiderivative, is tangent of theta. And then if I integrate 1 d theta, it gives me theta plus c. So this is not ideal. And this is something, this is something that we did not have to deal with in our last question. On our last question, we didn't end up with a theta. But remember, this is my final answer in terms of theta, but now I need to take that final answer and turn it back into in terms of x. So that's what I have to do now, and I have to actually solve for theta. I'm going to go ahead and make the triangle just like I did last time, and then we'll get to that pesky little theta in a moment. Again, last time, this is how we did it. We said x is equal to 5 secant theta. So we said x over 5 is equal to secant theta. Well, what is secant? Secant is 1 over cosine. And therefore, if I do the reciprocal of each side, I get 5 over x is equal to cosine of theta. So that's going to help me with wherever I decide to put theta, which has to be one of the acute angles. Cosine, if you'll recall, is adjacent over hypotenuse. And therefore, according to my picture, this guy would be 5 and this guy would be x. Just like I did last time, let's just do the Pythagorean theorem. We'll just call this side b again. So b squared plus 5 squared is equal to x squared. So b squared is equal to x squared minus 25. And then b is equal to root x squared minus 25. So again, that's this missing side. X squared minus 25. And again, we need all of that so that we can plug everything back in, because obviously we're going to be using tangent of theta. Now, before I can finish this up, this is sort of a, obviously this was step 5, we can call this step 5b. Step 5b is that I have to solve for theta. So I'm going to use what I had here. X over 5 is equal to secant of theta, and say if I need to isolate theta, how would I do that? Well, I could take arcsecant of each side, and if I take arcsecant of secant theta, guess what I get? That's right, theta. So theta is equal to arcsecant x over 5. So now step 6 is to just plug everything back in. I have a 5 times tangent of theta. So from theta, tangent is opposite over adjacent. And then I have 5, because remember the 5 is distributed, times theta, which is arcsecant of x over 5. And really the only other thing that I would do is cancel the 5's on my first part of my expression. So this is root x squared minus 25 minus 5 arcsecant x over 5, and I forgot the plus c over here. Plus c. That is my final answer. Let's now try an example for the last pattern. The last pattern is if the integral involves root a squared plus u squared, or remember this can be in either order because addition is commutative. And so as you can see from this question, we actually have the u value happening first. So again, if this is the pattern that I'm using, then u squared is equal to 9x squared. Therefore, u must be 3x. And 1 must be equal to a squared, and therefore a must be equal to 1. And if you'll notice on this question, they didn't tell me what to use to substitute. And that's okay, because they did tell me that I'm just going to let u equal to a tangent theta. So I'm going to let u, 3x, equal a, which is 1, tangent theta. So x, by division, is going to be 1/3 of tangent theta. So from here, let's get started on our same steps. I'm going to find dx. So if x is 1/3 tangent theta, then dx is 1/3 secant squared theta, d theta. And I need to find the substitution for 9x squared plus 1. And again, I can do that because they tell me it's going to be a secant theta, and a was 1, so this is just going to be secant theta. So again, I could plug it all in and show all of the work as we did in our first example, but I don't need to because someone much smarter than you or I came up with these great formulas and found the pattern for us. Step 3 is to replace everything I can in my original expression in terms of theta. So dx is going to be replaced with 1/3 secant squared theta, d theta. 9x squared plus 1 is replaced with secant theta, and that's all I have to replace. So now let's continue to reduce. I've got a secant theta and one of the secant thetas in the numerator that cancel. And I'm going to write my 1/3 out front. So I have 1/3, and then I'm left with secant theta d theta. And then I'm just going to integrate. And when I integrate, I get 1/3 natural log of secant theta plus tangent theta plus c. Again, if you don't know the secant rule, just get your integral table out. It should have your solution for you. Step 5 is to make our triangle. Again, choose a side to be theta, and then use what we know. So if tangent theta is equal to 3x, then I can say tangent of theta, tangent which is opposite over hypotenuse, is equal to 3x over 1. And so, using the Pythagorean theorem, whoops, don't do the square root yet, sorry. 1 squared plus 3x quantity squared is equal to the hypotenuse squared. And so, of course, 1 plus 9x squared is equal to h squared, and root 1 plus 9x squared is equal to h. And I can write that in either order, as we said before, 9x squared plus 1. I'm just going to do that because it's the order that it was written in to begin with. So that's step 5. And then step 6 is to replace. So my answer is 1/3 natural log. Now, secant of theta is 1 over cosine. And so cosine of theta would be, 1 over 9x squared plus 1. So secant of theta is root 9x squared plus 1. Now you don't have to write all of that out, I'm just doing that for your benefit. 9x squared plus 1. And then tangent of theta, tangent is opposite over adjacent, so that's tangent of theta is 3x over 1, which is just 3x. So plus 3x, and then plus c. And that is my final answer. If we are lucky enough to have an integral that is only a radical with one of our special patterns, which means it's not a denominator, there's no other factors involved in our integrand, then we actually get to use a special integration formula, and we don't actually have to do any work except for determine what is a, what is u, and what is du. So let's take a look at this example. I can see that this is the integral of 9 plus 4x squared dx, and so obviously I'm going to use this third special integration formula. And it doesn't matter that my a and my u are switched around. A squared is 9, so a is 3. U squared is 4x squared, so u is 2x. And then du is the derivative of 2x, which is 2 dx. Now this part is really the most important part, or the easiest part to, I guess, mess up on, because if you forget to find that du is 2 dx, then you will forget that there needs to be then a 2, so that there's a 2 dx inside the integral, and you'll forget that there's then a 1/2 on the outside of the integral, and your answer will be off by a half everywhere. So again, I've got a half. I'm going to actually keep that one in yellow so you remember that that's where that 1/2 came from. And then I'm just going to copy this formula exactly and replace u's with 2x and a's with 3. So this one says 1/2, so that's this 1/2, whereas this one is this 1/2. 1/2, and then that's times everything, so u is 2x, square root of u squared plus a squared, so I'm going to keep it in the same order as the original question for continuity, plus a squared, which is 9, natural log of the absolute value of u, which is 2x, plus root, and again I'm going to keep it in the 9 plus 4x squared form, and then plus c. So now the only thing I have to do, oops, parenthesis there. Now the only thing I have to do is clean it up a little bit, and then I'm going to be done. So obviously this is 1/2 times 1/2, so really I'm taking 1/4 times everything. So 1/4 times 2x is 2x over 4, or x over 2. And then I've got root 9 plus 4x squared. And then I have 1/4 times 9, so that's 9/4, natural log of 2x plus root 9 plus 4x squared, and then plus c. And that is my final answer. And I challenge you to go ahead and try to find the answer to that using the method we had before, and you will see how much work it would have taken, whereas here all I have to do is plug and chug. Coming up next, we are going to take a look at how we use partial fractions with linear factors to integrate.